Hi everybody, we're going to do one example of a rational function with wholes. We haven't gotten there yet. So we're going to practice an example with wholes, and then you guys are just going to work through the rest of the problems in the student note packet. So I'm on the blue section, chapter 4, page 17 of the student note packet. We're going to do example 1 together, and then you guys will finish the rest of the pages that relate to wholly rational functions. So number 1 looks like this. We've got this super long function, and this is going to be closer to the type of question you guys will see on your test. So up until now, I think we've done some relatively less complicated rational functions. This one's going to require a couple of more steps. We're just going to work our way through all of the information, starting with the wholes, and then we'll put it all together in a graph. So I'm going to start here on this blank page because we've got some factoring to do to see if we can find wholes, and then we'll go from there. So if I were to factor this, we've got to factor the top and the bottom. And here's the deal. On your test, when you get something that looks like this, we want to be really, really careful about factoring because we need it to be correct. If you get the factoring wrong, then everything else kind of is an effect of getting the factoring wrong. And ultimately, right, all of those things on the test will be incorrect. So we want to make sure that the factoring is good before we go any further. So 3x squared minus 3x, I can pull a 3x out of both of those terms. And that leaves me with x minus 1. And then x squared plus x minus 6, I can factor that into x plus 3 and x minus 2. All right, so that's the top fully factored. And then the bottom, x squared minus 6x plus 8, that's going to factor into x minus 2 times x minus 4. And then x squared plus 4x plus 3, x plus 1, x plus 3. So we've got this fully factored, and the first thing we're going to look for are those wholes. Now remember that the wholes come from places where our factors canceled on the top and the bottom. So we're looking for factors that are exactly the same on the top and the bottom. So I've got 1, x minus 2, I can cancel on the top and the bottom. I can also cancel x plus 3 in the top and the bottom. And it looks like those are the only two things I can cancel. So we have two factors that are going to contribute to wholes. So the first factor was x plus 3. The second is x minus 2. I'm going to set both of these equal to 0 and solve for x. So in this case, we have a whole when x is negative 3, and we also have a whole when x is positive 2. Now, wholes are points on our graph where our function is undefined, but they're points. They're not asymptotes. So it's just a single point on our graph where our function is undefined. So what we have to do is we actually have to express wholes as ordered pairs. X equals negative 3. That doesn't work for a whole. We need a single point. So I need an x and a y value to express an ordered pair. So what we're going to do is we're going to take the x values we just found, and we're going to go back to our simplified function. And this is where it gets a little tricky. From here on out, as soon as we found the wholes, we are only now going to use the simplified function. So I'm only working with the pieces of my function that we didn't cross out, those factors that remain after we've crossed out the wholes. And what we're going to do to find the y values of these wholes is we're going to plug in negative 3 and 2 for x and get y. Now we're using the simplified function because if I use the original function, we're going to get 0 on the bottom, and we can't divide by 0. So we get this weird thing that doesn't give us any information about where the whole is. All right, so simplified function from here on out, we'll use that simplified function to find the zeros, the asymptotes, everything like that, and then also to perform the long division for the non-vertical asymptote. All right, so when x is negative 3, we're going to get 3 times negative 3, and negative 3 minus 1 over negative 3 minus 4 times negative 3 plus 1. All right, that is going to be, let's see, 3 times negative 3 times negative 4, which is 36. And then in the denominator, it looks like we've got negative 7 times negative 2, which is positive 14. And I'm going to express this as a fraction in simplified form, so 18 over 7. So our whole is negative 3 18 over 7. Then I'm going to do the same thing when x is 2. We're going to have 3 times 2 minus 1 over 2 minus 4 times 2 plus 1. All right, so that becomes 6 over negative 6, which is negative 1 there. So our second hole is at 2, negative 1. So our two holes are these points here. Okay, now on a test, when you're given an equation with a hole, I need to see all that work. So make sure you guys are showing the work to get credit for that. All right, next up we've got our zeros. So remember that the zeros occur when the numerator of our function is equal to 0. Now we're taking the simplified function and using that from here on out. So there are two zeros, one when x is 0 and the other when x is 1. All right, two factors in the top, 3x and x minus 1. Set each of those equal to 0, solve for x to get the zeros. Remember that those are also points on the graph, so we represent those as ordered pairs as well. Not a whole lot of work to show for those. Okay, moving on, we've got our vertical asymptotes. Those come from the factors in the denominator that make the denominator equal to 0. So two vertical asymptotes here, x is equal to 4 and x is equal to negative 1. All right, I'm going to move on to the next slide and continue the work there. So I've put in the whole zeros vertical asymptotes that we just found on the last slide, and I've also included the simplified function in the top in blue. So the next piece is the y-intercept. Remember, the y-intercept we find when x is 0, so just plug 0 back in, and we actually have it as a 0 as well, 0, 0. When x is 0, y is 0 here. And so then we move on to our sign chart. Now our sign chart is going to include those critical points. Those come from the zeros and the vertical asymptotes. So it looks like we're going to have negative 1, 0, 1, and 4. And then I'm going to make sure I include the infinities to kind of give us a better idea that those are the intervals where we're looking at end behavior as well. And I'm going to use the sign, the shortcut for the sign chart. So there were no double zeros or double vertical asymptotes. There were no factors in the top and the bottom that were being raised to an even power. So I know that as soon as I find the first interval, that my signs are just going to alternate on the sign chart because there's no double zeros or double vertical asymptotes. So if I start on the interval negative infinity to negative 1, and I look for the sign of the function on that interval, I'm just going to plug in a really negative number for x. And in the top at its core, we've got x squared. In the bottom at its core, we also have x squared. So any negative number squared is positive, which means that the top and bottom will both be positive of this function when x is really negative. So our first interval is positive, and then negative, and then positive, negative, positive. I know that we alternate again because there were no factors in the numerator or the denominator that were being raised to an even power. That would create a double zero or a double asymptote. Next up, we've got the non-vertical asymptote. So again, everything underneath this sign chart is going to come from the long division. So before I do that, I actually need to distribute this and FOIL the bottom. We're going to get 3x squared minus 3x all over x squared minus 3x minus 4. And so that is what I'm going to perform the long division with. So 3x squared minus 3x is going to go into the hat. X squared minus 3x minus 4 is going to go on the outside. And the question is, what are we multiplying x squared by in order to get to 3x squared? And the answer is positive 3. I'm going to multiply the divisor by that. We get 3x squared minus 9x minus 12. And remember, we're subtracting everything there. So when I add everything together, or subtract everything technically, negative 3x plus 9x is going to become 6x's plus 12. So my new form of the function after we perform long division is going to be 3, that quotient, plus the remainder over the divisor. All right, so that's the second form of the function. So in math, like if you think back to fractions, the first way that we had our function expressed, at the very top, that would be like the improper fraction, right? If I have the fraction 11 over 7, that essentially is the improper fraction form. And then when we go down here, after we perform the long division, if I were to write 11 over 7 as a mixed number, that'd be 1 4/7. That's the mixed number form, which is like the second form of this function, right? That would be more like the mixed number form if we're looking at it in terms of how we know fractions. Each are exactly the same. They give us the same value, but they give us different pieces of information. So our non-vertical asymptote is always y is equal to our quotient. So in this case, y is equal to 3. And then we go to find the intersection point. So remember that the intersection point, we take the numerator of the remainder and we set it equal to 0 and solve for x. So 6x plus 12, I'm going to set that equal to 0 and solve for x. In this case, x is equal to -2. So again, the intersection point is a point on our graph, so we need to also find a way to represent that as an ordered pair. We take the x value we find in the intersection point, we go up to the non-vertical asymptote equation, we plug it in for x to get y. Now in this case, again, we don't have anything to plug in for x, so y is always going to equal 3. So the intersection point occurs at -2, 3. And then the last piece, that end behavior, we always approach our non-vertical asymptote. We've just got to figure out from above or below. And the last piece is going to require us to plug in a really positive number and a really negative number to the whole entire fraction that comes after the quotient. So I'm going to plug in a really negative number for x into 6x plus 12 over x squared minus 3x minus 4. If I plug in a really negative number there, I get a negative on the top and a positive on the bottom. So that is negative, which means we're going to be approaching our non-vertical asymptote from below as x goes to -infinity. So on the left side of our graph, when we go to graph this all, we're going to be coming from below, approaching that horizontal line at y is equal to 3. All right, last one. I'm going to plug in a super positive number for x into the fraction after the quotient. And when I do that, we get positive over positive. So in this case, we're going to be approaching that horizontal asymptote from above. Okay, we've got all of this information. Now we're just going to move over to the graph. So I've moved all of the information here with the graph, and I've got my axes, so let's go for it. I'm going to scale by 1 here, and I'm just going to go down the row. So holes, first up. When we graph holes, we're going to graph them with open circles because they're places where our function is undefined. So 2, -1 is one hole. And then -3, 18 over 7 is our second hole. And you're just going to, estimate there. Okay. 0, 0, 0, and 1, 0. So our zeros are places where our function is defined. They're points that are defined. So we're going to include those as closed circles. So 0, 0, 1, 0. Pretty close together here. And then vertical asymptotes, x is equal to 4 and -1. We have a y-intercept at 0, 0, which we've already graphed. I'm going to come back to the sign chart. We've got a non-vertical asymptote at y is equal to 3. We've got a horizontal line here. And then an intersection of our function and the non-vertical asymptote at -2, 3. So -2, 3, we've got a point that sits on that horizontal line. These are our real points. Our function is defined at this point, so we also include those intersection points as closed circles. First interval we're going to start with is -infinity to -1. So this is one of the components of the end behavior. The only two intervals, far left, far right, that we also have to include end behavior. This is the first one. So -infinity to -1 means everything to the left of that first vertical asymptote at -1. We are positive, which means our function needs to be above the x-axis. And then we also have to consult the end behavior. As x approaches -infinity, we are going to be approaching our non-vertical asymptote from below. So above the x-axis, below the non-vertical asymptote as x gets smaller and smaller. But in this interval, we also cross the non-vertical asymptote. So this one gets a little bit more complicated. We always follow asymptotes. So I'm going to start up here. We know that our function is going to be going all the way up to positive infinity along that asymptote x is equal to -1. We're going to come down, we're going to cross at that point where we intersect with the function and the non-vertical asymptote, and then we also have to go through the hole. So we have a hole, we always want to make sure we don't skip it, and then our function is just going to come up, and as x goes to -infinity, we're just going to follow the non-vertical asymptote from below. On a test, if you were to have drawn that function like that, I would take points off. So the end behavior is there to tell us how the graph is going to behave, the far left and the far right. So on the far left, in this case, we are always going to be approaching that non-vertical asymptote from below, but we're going to stick really close to it. In all of these places, our graph is still positive from the sign chart, still above the x-axis. And then, like I said, we've gone through that hole, that intersection point, and then we're following the vertical asymptote all the way up to positive infinity for the y values. Next interval, -1 to 0. Now we're in the middle, which means we don't need to look at the end behavior. For the middle intervals, the end behavior doesn't matter. -1 to 0, we are negative. So from -1 to 0, that means we've got a really small place in our graph where we're going to represent that. We're just going to go down, follow that asymptote, x is equal to -1. And then from 0 to 1, we're positive. So we're going to kind of pop up and come back down to the other 0. And then from 1 to 4, so between the second 0 and our next vertical asymptote, our function's negative. So we're going to come down, make sure that we hit that hole, and then we'll go down on that side as well. Follow the other asymptotes. It's kind of like a very lopsided parabola-ish. And then the very last interval from 4 to infinity, which means we're to the right of that vertical asymptote now, our function is positive, so we need to be above the x-axis. We're also dealing with the far right interval, which means we're looking at end behavior as well. The end behavior tells us that we're approaching from above the non-vertical asymptote. So above the x-axis, above the non-vertical asymptote, means our last piece of the function is sitting right there. All right, that's it. Holes, more zeros, more vertical asymptotes than maybe we've seen before, slightly longer sign chart. The only thing that's going to get more complicated is the non-vertical asymptote equation, which we'll see in the next lecture.